All right, this is 5-4. It's the only day we're going to spend on it. Entitled the number e in the graph e to the x. I want to build up to that idea in a couple of slides here. We're going to talk about the concept of interest and compound interest, because e is really kind of a specific type of compound interest. I should say compound interest, but a special type of exponential growth or decay that can come up with interest. So here's what we're talking about. All right, when we're talking about compounding interest, we really need to identify n. What's your compounding period? Okay, let's just think in the context of an investment. Okay, this is a pretty significant thing. Your interest is your growth. Okay, now when interest is compounded, that means there comes a certain point in time when the growth of your investment is added to what's called your principal. Here we're just calling that the original amount. Okay, so then in the next period, you get a percent of that new bigger amount. Okay, again, P is that original amount, R is your rate, N is the compounding period. Okay, and we just have to be very good about identifying what that period is. Okay, we have an example right at the bottom here that says we invest $1,000 at 5%. Here's the key phrase: compounded quarterly. That means 4 times a year. So if our investment's growing at 5%, that means every 3 months. And that's coming from 4 times a year. We get 5% of our original amount added. Okay? But that amount changes each compounding period. Okay? So if I want the amount here, P is 1,000. I need to do 1 plus because this needs to be a growth model. And if I just did my rate of 0.05, that would make it a decay model. Anytime you see an interest rate, though, it's per year. Okay, so we don't get 5% of $1,000, we get 1/4 of it. And then as far as the power goes, this is going to be 4 times 10. Okay? Interest is going to be added to our investment 4 times a year for 10 years. Oh, and at this point, it really just kind of becomes a calculator thing. You type it all into your calculator and just see what it gets you. $1,643, and we'll round up 62 cents. Okay? Not a staggering amount of money, but that's largely because the original investment wasn't that big. You wouldn't expect to. And it's not bad. Over 10 years, we gained about $643 from investing 1,000. That's not too bad. All right, now, notice right here, because we're going to talk about the number E now, it has a very, very similar structure to the rate of compound interest that we just looked at. Okay? Now, in the example we just did, N was 4. Okay? But we could look at bigger values for N. You'll see some problems where interest is compounded monthly. There, N would be 12. Sometimes interest is compounded daily. There, N would be 365. We could check bigger and bigger and bigger values for N. Okay? Your homework assignment has you do this. It has you check numbers like 5, and then 50, and then 5,000. What if we made N 5 million? As we put in bigger and bigger numbers for N, we'd see the overall value hits a limit. It doesn't get past about 2.71. Okay? That leads us to this new base called E. And it's used for models that represent continuous growth or continuous decay. We have some similarities here. P sub O is the original amount invested. But here's where we see some differences. Notice where the rate is. It's up in the exponent now because continual problems that involve e, they use e as the base. Okay, the rate isn't in the base anymore. T is still time. Now, before we get to any kind of word problems with e, I want to emphasize here that e is a number, and we can evaluate expressions that have e. And throughout all these, it's good to just envision that e is about 2.71. It's kind of like with pi, how a lot of times we'll use 3.14. Even though pi is this long decimal that goes on forever, e is the same way. But we just round it to 2 decimal places. There is a button on the calculator for e. I can show that to you in class if you're not familiar with where it is, but e to the third power is like a little bit bigger than 20. I think it's good to be aware that e has this value and we can evaluate expressions with it. Properties of exponents still apply. E to the negative fifth is 1 over e to the fifth. This I'm expecting to be a small little decimal, and it is. It's right around 0.0067. E to the first is about 2.71, and e to the 0, that follows that same property of exponent that all bases do. Anything to the 0 power is 1. Always has been, always will be. Okay? Let's talk about some word problems here. Okay? I want you to know, this is a population model, but it doesn't have a compounding period. Okay? A lot of times populations just are continually growing. Certain people are moving in, certain people are leaving, okay? But a city or a town experiences a population growth if more people are moving in or more people are being born than are leaving, okay? 5,000 is our original amount. Now keep in mind here, we're talking people, not money, so make that shift. This is 5,000 people. The population in 25 years just involves evaluating at 25. Okay? I just want you to see here that the growth rate is 5%, and notice that we don't have to make it 1.05. That's because we're using e as the base. E is like 2.71, so we already have a base that's bigger than 1. This is a growth model. Okay? If we wanted to make it a decay model, we would make the rate negative. But this is a growth model. 5,000 times e to the 0.05 times 25 power. I know that's not a super complicated problem, but given that it's structured a little bit differently from a compound interest problem, I wanted you to see that. Okay. New population after 25 years would be about 17,452 people. Okay. All right, last slide down here. I'm going to set these up, but I'm going to let you come to the final answer here. Okay. We have 3 different scenarios. Plan A, Plan B, and Plan C, and they all involve investments of $1,000 for 6 years, and we just want to see which one is the best. A of 6, okay, 5.45% compounded daily for 6 years. Okay, $1,000 invested. Notice this is not a continuous model. We're not using base E. We're taking 0.0545. That rate has to get divided amongst all 365 days, and then we raise it to the 6 times 365 power. Okay, whatever value we get for that, that's how much that investment would be worth after 6 years. B of 6. Similar setup now, but now we're compounding quarterly. Original investment is still the same. It's $1,000. 0.065 over 4, because interest is being compounded 4 times per year to the 4 times 6 power. Okay? Again, I'm leaving you to evaluate these yourself. to come to the conclusion as to, which one's the best. C of 6. Continuous. All right, $1,000 invested. The base is E. Make sure you have that connection, that continuous growth or decay. We've been mostly looking at growth models today. Involves base E. 0.0625 is our rate. And then we evaluate that to the 6th power. Okay? Go ahead and evaluate those. The calculator is going to come in handy and see if you can come to the conclusion as to which one of those plans leaves you with the most money after 6 years.